Also, besides the electric motor operators that we just showed there, if you have pneumatic linear glow valves, or you have even rotary, any type of rotary glow valve, there's many companies that make limit switches. Probably Westlock is the best known out there. But limit switches, which typically are if you look at these packages here, inside these enclosures, there typically are 2 micro switches in there that will send a signal back to a full open or full closed position. And the other nice thing about these is they have visual indicators on top that will tell you if the valve is open or closed. So these limit switches, they're available in just about every configuration you can imagine. Again, they'll give you indication locally at the valve and also remotely back in the control room. The next item on our agenda is wireless steam trap and valve leakage monitoring system. That seems like a mouthful there, but wireless signals are becoming more and more prevalent. Not necessarily for control, but definitely for monitoring and for some safety reasons and some energy savings and things like that. In this case, we represent a company called Cypress Envirosystems, and they've come up with what I think is an ingenious concept and product here. What they're doing is they actually have a wireless transmitter that is connected to 2 temperature sensors that can be strapped on the upstream and downstream side of a key steam trap, or you actually can do this to any valve too if you have a valve that's very important that you do not want to leak. And this controller here, the wireless controller, will actually do the math of the temperature differential to determine if it starts seeing the same temperature both upstream and downstream, and that valve is supposed to be closed, and the logistics would tell you that that valve is leaking. This particular package comes with its own software. It has its own monitoring system that you can do this. It's got an easy setup, and again, it's wireless. So all you have to do is get this thing set up out there at the valve, and it will send the signal back to your control stations. And again, you can look at your steam traps, what their health is. You can look at a valve and see what its health is. You actually can track the data to see if a valve's leak is getting worse. You might start to leak and you go, well, it's not bad yet. We'll just monitor this, and maybe 8 months later you notice that the temperature seems to be going up on the downstream side. So you're starting to see that the valve's leaking more, and for the next outage you would schedule some maintenance on that valve. Now, again, with steam traps or anything like that, this next slide here will show you that there's a lot of energy loss there with steam traps and any valve that's handling steam, because you go to so much effort and energy and cost to heat up the water to steam. It's when they fail, when these steam traps fail open, there's a lot of energy loss very, very quickly through those. So, not to mention the hazardous working conditions. The failed trap cost in a steam trap could actually be quite high. In this case, a single steam trap would actually failed open would actually be about $6,640 of energy costs lost per steam trap. So there's a lot of steam traps out there, and a lot of, and I use the steam trap analogy here to valves because actually a steam trap actually is an automatic valve. It either uses a temperature sensor or a thermodynamic sensor to open and close to open up and remove the condensate from the steam line. So in reality, it is an automated self-contained valve. Okay, the next item on our agenda is, are your pneumatically operated valves working properly? And this is a little bit of another departure from kind of the areas we were talking about, and again, that might seem like a silly question, but the concept here is that many automated valves run in the open position most of the time. There's a lot of process chemical plants out there that their key valves, either running for steam or for chemicals that are very expensive, are in the open position most of the time. And when it comes time to close those valves, that could be once every 6 months or once every 3 months, or in some cases it might just be for an emergency shutdown when you know that valve has to close. So the question is, do you know that valve is actually going to move, and when you cut the air off of it, will that thing actually close, or will it be potentially stuck open for a variety of causes? You know, I mentioned earlier about there's a thing called stiction that happens, especially in rotary valves, when in the ball valves, when they get into that full open position and they've been sitting there for months, they tend to get in the locked position, and so the breakaway torque increases quite a bit at that point. So there's a chance where a critical valve or some critical valves could be actually left in a open position, and when you need them to close, they just don't make it. There's a new technology out that's called partial stroke testing, and it actually is an automatic partial stroke testing. There's several companies that are making this. TopWorks, Fisher has it, Mason has it. These are also called emergency shutdown apparatuses. They look like or actually they are a part of the digital valve positioner family that we spoke about earlier, the smart positioners. They actually have been adapted to be used in conjunction with a programmable logic controller to be able to test a regular on-off automated valve while it's in line or while it's still running the process. So as it says here, these digital valve positioners can be installed on an automated on-off valve, and you can program them to test your actuator and your valve performance while everything is still running. The next slide is going to give you a schematic of how this actually works. To the right up here is your programmable logic controller. This is set up to, on a timed basis, we'll send the signal out to the digital controller, and it will, if this valve essentially was open all the way, it would hit this solenoid valve to exhaust some of the air out, and it will take that valve from full open maybe down to about 70% open. And then it would actually look at a lot of different factors while it's doing that, how well that moved, whether it's stuck or not, whether it was a delay when the air exhausted. And it gives all that information back to the controller and actually tells you the health of that valve. I mentioned about going down to about 70%. In some cases in a process chemical plant, maybe at night, they don't run the full range of the process. So that would be a good time to have it pre-programmed to automatically take selected valves. They can be done one at a time or whatever you do it. And you can see in this graph here, this took a valve that was fully open, and it took it down to about 70% open and back. And look at all the information that came back. It came back with how much friction there was, what the breakaway pressure was, what the response time was, and I mean, this is amazing how much information you get about the health of your automated valves. And not only is this a safety situation, but it's you're going to be saving lost energy if these valves get stuck open and you can't get them shut. So there's multiple features here, and this technology is I think really fascinating and encouraging to see how smart the controllers have become now. Okay, we're going to be going on to our last program item, and this is another switch in vertical markets. We're going to be looking at the building management energy savings. This is for anybody who is involved with maybe campuses or HVAC applications for either large office buildings or multi-building sites, or if you run a steam or chilled water cooling plant down in a metropolitan area, and you feed maybe 6 hospitals with all that energy, either the chilled water or the heat. The actual technology that you or the goal of a building energy management team is to try to maximize the differential temperature of the flow going out to an air handler versus the return flow temperature. And this is true of either heating or cooling. As an example, if you come out of your chillers and you're sending 50-degree chilled water out to a building to cool it, you would want that return water temperature, to be in the 70-degree range. You want the most differential temperature you can get, the better it is. The problem is that as the downstream demands change, trying to balance the energy load is very difficult. And what I mean by the demand changes is, if you were in a, let's say, like a university campus, and suddenly one of the big meeting halls was opened up and it had been closed overnight, and suddenly they need to cool this room down from 85 degrees down to 72, and that's going to put a big load on the chillers. Consequently, the pump speed will change. Auxiliary pumps may kick in, and they will do everything they can to create the head pressure that's required to try to meet the demand of that. We represent a control valve company called Warren Controls. They're a domestic company. They're one of the best control valve manufacturers in the United States. And they have come up with an ingenious concept. It's called pressure-independent control valves. And what it actually is, it is an industrial grade assembly comprised of two pressure-balanced valve bodies. The first one on the left there is actually a traditional control valve that has an electric motor actuator, and it's a very high thrust electric motor to actually control the flow. Now, if that was used by itself, that would be trying to react to the different pressures that are coming into that valve, and if by itself it would not do a very good job. The second tandem valve is actually a pressure differential control valve, and it is a spring-loaded and mechanically actuated valve that reacts to the differential pressure across that control valve. So the two of these actually work in tandem, and the concept is to try to keep the differential pressure across that valve balanced. And you'll see later on, if you can control that, your energy efficiency will be improved dramatically. I'm not going to go into a lot of details on this. If you're interested in this product, this does need quite a bit of engineering from the Warren Controls engineering people. They can help you size this, and it does need to be sized very accurately. But the concept is the primary influence is to a flow of fluid through a control valve that is reacting to a control signal. It will move based off the upstream and downstream pressure changes. So if you just use a normal control valve, the flow will increase if the differential pressure is raised and will decrease if the differential pressure is lower. And a plain control valve changes to the differential pressure across the valve affects flow in an undesired and nonlinear way. So you will not get your optimized control if you're just using a plain control valve. Changes in pump pressures can produce changes in flow rates, and they may not even be related to the system controller's output signal. So if you can control this and actually compensate for the pressure changes, you will have results of much more predictable and stable flows.